Okay, physics. Thought I'd do a couple of problems, just walk you through these and get you accustomed to how I solve these. Sometimes it helps to see a couple of these done to organize your thoughts and get accustomed to what to do when you don't know what to do. So, to to be fair, I looked through the college textbook, the one actually my son's using this year, and I picked two problems that look complex, but I have not worked these beforehand, so I don't know the answer, and I don't know how to go about these yet. So you'll get to see me struggle as well. So first one I was going to do is number 64. So 64 says, oh, this is Physics for Scientists and Engineers by Randall Knight. Okay, 64 says Bob is driving the getaway car after a big bank robbery. Poor Bob. Poor choices. He's going 50 meters per second when his headlights suddenly realize, okay, well, I got to draw a diagram. So I'm not sure what's going on. Let's see. So he's going to be driving on a road. He's got a car. Right there it is. He's inside the car. He's going at 50 meters per second. I don't know anything yet, but I'm going to say this is going to be the positive direction. And I know the initial velocity that he starts with is going to be 50 meters per second. Okay. His headlights suddenly reveal a nail strip. Oh no, the cops have placed across the road 150 meters in front of him. Okay, so nail strip. There it is. Nail, nail. That's a nail. That's a nail. And the distance here between the car and the nail strip is 150 meters. Okay. So I don't know if I'm going to use this yet, so I'm going to put this off to the side. So my change in distance that I might be worried about is 150 meters. If Bob can stop in time, he can throw the car in reverse and escape. Yeah, good luck. But if he crosses the nail strip, all his tires will go flat and he'll be caught. Oh, we don't want Bob to get caught. Bob's reaction, oh, maybe we do. Bob's reaction time before he can hit the brakes is 0.6 seconds. Oh, reaction time, right? So there's going to be some time in here before he does anything, 0.60 seconds. And his car's maximum deceleration, so I'm going to call this negative acceleration. So the acceleration is going to be in the opposite direction at 10 meters per second squared. So right, they call it deceleration. I want to be careful about this, right? So if I'm going in this direction with positive velocity, acceleration is going in the opposite direction. So I'm going to be careful with my signs, make sure I get that right. Does Bob stop before? So I want to figure out how far it's going to take. So what I want to find, and they throw me a little curveball. So what I want to find is I want to find how long is it going to take him to come to a stop, right? So given this acceleration and this velocity going to 0 meters per second, I want to find time. Nope, I don't want to find time. Does he? Does he stop? So I want to find distance. Yeah, I want to find distance. All right, so distance. Can I do this? Well, sure. I'm going to be careful though, because that distance isn't going to be my answer, right? They tell me that he's going to travel for 0.6 seconds before he hits the brakes, right? So I'm going to do two things. First thing, I'm going to use this information to figure out how far he travels after he hits the brakes, and then I'm going to do a second question to figure out, well, how far did he travel before he hit the brakes? Right, so in this case, I have constant velocity. Right, he's going at 50 meters per second. And right, so I'm going to forget about that total distance. So I want to find the distance he travels at constant velocity. And then when I add those two together, I want to see if that's going to be less than 150 meters. And if it is, then I'll go back and figure out how much shorter he is. Okay, well, a little bit of math. So I'm going to look at my equations. Remember, I have three equations to choose from. I know that x is going to be x naught plus v naught t plus 1/2 at squared. I know, what else do I know? V squared equals v naught squared plus 2a delta x. Right, so that's the second one. Let's see, so this one doesn't have final velocity, this one doesn't have time. So, what's my third one? Oh, it's the definition of acceleration. So v is going to be v naught plus at. Okay, so those are the three equations I have to choose from, and I'm going to use one or more of these to help me get to the answer. So I'm going to hunt. I know initial velocity, final velocity, acceleration. I want to know change in time, so I think I'm going to use this one. So I'm going to say, so these are my givens. This is my unknown I'm looking for. The equation I'm going to use, I'm going to write the equation first and then solve it. So the equation I'm going to use is this one. Right, I'm going to solve for this whole thing. So I could have my final position minus my initial position in here for delta x, but I want to find how far I've traveled, so I'm going to keep it together and treat it as one variable. And I'm going to drop the delta because it gets tiresome to write these things. I want to solve for the delta x, or I'm going to call it x. So I'm going to flip things around. I'm going to say 2a times x is going to equal v squared minus v naught squared. Convince yourself that makes sense. And I'm going to divide by 2a. So I'm going to divide both sides by 2a. Right, algebra. I'm going to have x is going to be equal to v squared minus v naught squared over 2a. Don't plug in numbers, right? Trust me. I'm going to give you a lot of questions where I'm not giving you numbers. And if you get comfortable doing this, even when you have numbers, then you'll make fewer mistakes, and it'll help you. And it's recreational algebras, right? How could you not enjoy it? Okay, so now I'm going to plug in some numbers, right? So I've solved this. Now I'm going to plug in some numbers. I got v squared, which is 0, so I'm going to have negative 10 squared over 2 times negative 10. Right? So notice I'm going to end up with a positive number, which is good because he's moving forward and his displacement should be in the forward positive direction. Right? So I'm going to have, right, I'm going to put parentheses around this. Okay, so I'm going to have 100 divided by 20. I'm going to call this 5. Oh, I'm sorry, I missed 50. This is 50. So 50 squared is what, 2,500. Yeah, that seems like more sense. There's a 0, so 125. 125 meters. Right? And I'm going to circle that because that's the information I care about. Right? All right, so I didn't plug in the right numbers here. But when you do that, you get a ridiculously small number. Right? So the mistake I made was I put in 10 for the initial velocity. Should have been 50. And then you get a really small number of, in my head I was coming up with 5 meters, and I realized you must have gone further than 5 meters, so I went back to check to see. Okay, so that's part of my answer. It's not the whole answer, so let me go on to the rest of it. So these are my givens for this second part. So my unknown, I want to write the equation, so I'm just going to use the definition for velocity, right? So velocity is going to be the change in distance over time. So I'm going to solve that. So I'm interested in change in position, so it's going to be velocity times time. So now I'm going to plug in some numbers, and I'm going to have 50 times 0.6. What's that going to be? 30? So 30 meters. Okay. So that's my second answer. When I combine these two together, right, I'm going to end up with 155 meters. Does he stop in time? No. But if you didn't do the second part, to remember that he took him 0.6 seconds to apply the brakes. If you didn't remember that, then you wouldn't have come up with that correct answer. Anyway, I think I'll do a second video for the second question that I was going to do for you. Anyway, hope that's helpful, and I hope that's the right answer. I haven't checked it, so we'll talk to you soon. Bye.